Hello and welcome to Richardson RFPD's Tech Chat. I'm Peter Dietrich, Senior Technical Sales Engineer at Richardson RFPD, here today talking with Brian Dubois, Wolfspeed's Application Engineer for Silicon Carbide modules. Thank you for joining us, Brian.
Yeah, thank you. It's good to be here.
In the power semiconductor industry, there is a growing interest in wide bandgap technologies, such as Silicon Carbide, a segment in which Wolfspeed is at home. In comparison to semiconductors based on silicon, Silicon Carbide enables high efficiency due to lower conductive losses, lower switching losses, and higher switching speed and frequency. But the switching behavior could become an issue for the EMI topic. Therefore, we are frequently asked about EMI emission of these devices compared to silicon. So I have a few questions related to this topic. Brian, maybe we can start with a general one. How does silicon carbide differ from silicon regarding the EMI?
All right, yeah, so that's a good question. And the first thing to understand is that all power electronics systems will produce emissions in some way. The question is how much and is it a problem? With silicon carbide, as you mentioned, you have a few advantages. You have the higher edge rates that enables higher efficiencies and also higher switching frequencies. But when you have systems that are switching faster and operating higher switching frequencies, you do have to consider how that's affecting your system in terms of EMI. So if you look over here on the left, we have some spectral waveforms here that basically shows how different types of waveforms produce emissions that persist at higher and higher switching frequencies. So if we imagine here, if we start with a 10 kilohertz fundamental frequency, if you imagine the slowest device possible would be a perfect triangle wave. And in that case, we would roll off quite quickly as we go up in frequency. If we go to a perfect waveform, which would be, infinitely fast switching with a square wave, then we roll off at 20 decibels per decade. An actual device is somewhere in between, more trapezoidal shaped. And the faster you switch, the more you approach that square wave and the more your emissions will persist at higher and higher frequencies, which can affect you when you're trying to meet compliance or if you're having issues with high frequency content affecting the surrounding systems. The second thing is that as you move up in switching frequency, you're moving your fundamental. And as you shift your fundamental around, that might affect, depending on what kind of standard you're meeting or how, where other equipment in your system is susceptible to, that can either help or hurt you, but it's just something that you have to consider as you move up to higher switching frequencies.
Okay, understood. This means that EMI should be considered as early as possible in the design phase in order to find the right compromise for all interfering parameters. In this case, what advantage do Wolfspeed's modules offer design engineer to compensate for the EMI emission? Or how do your modules help the customer relative to EMI optimization?
Yeah, so there are a few differences when you're designing a system with power modules versus, say, a typical discrete device. And the primary one is on how emissions can couple through the system. One thing about common mode currents is that they can couple through very surprising paths. That's maybe things you won't expect. And a common one is through the cooling loop. When you have your devices mounted to some sort of base plate or heat sink where you're trying to cool them, that heat sink is usually connected to the rest of the system. Maybe it's grounded or maybe it has a direct connection somewhere. And currents can actually couple from the MOSFETs through your electrical insulator and out to the surrounding system. You can see that here on the right where you have your equipment under test and your MOSFETs. It couples through the ceramic in this case and out to somewhere else in the system where it can cause issues. Now, this insulator I mentioned, so in a power module, this is usually a ceramic. So this is a stiff material that's part of the substrate. It's part of the module itself. And that's something the customer does not have to worry about. It's something the manufacturer, that we take care of. With a discrete device, typically the backside of the device is not insulated. It's still electrically conductive. So what you have to do is actually put in your own insulating pad between the device and your heatsink. Now, I know some manufacturers do make discrete devices that are insulated, but for the most part, most of them are not. Now, what does that mean? So for a power module, the ceramic is a very consistent rigid material, as I mentioned. So that means that we as a manufacturer can measure the parasitic capacitance, and we can provide that information to customers. And they know when they buy a module, this is the coupling that they're going to expect. For a discrete device, it depends. It's up to the customer in their system. They have to, generally the insulating pad might be a soft material. So maybe depending on how hard you clamp it down or some tolerances, it might change the capacitance. The number of die might change, how big your insulator is. It's something that's more system dependent. And so a designer is going to have to look at their system and measure their system to understand the emissions. And that's fundamentally different sides of the process. If you're designing with a module, you can start looking at EMI before you even buy the product. If you're working with non-insulated discrete products, then you're going to have to wait until you've already built your system to really understand what that coupling is going to look like.
That sounds great. So finally, how does Wolfspeed help the customer with the design? Or what kind of tools does Wolfspeed offer to predict EMI and simplify the design in work?
Yeah, so the primary tool we offer is we enable our SPICE models that we provide to customers to do these EMC simulations. Effectively, when we make our power module models, we characterize the base plate capacitance coupling, and we put those parameters inside our power module models. You can see here, there's a base plate pin on the module. That's not for thermal reasons, that's all electrical. So customers can take our power module models off our website and they can build them into, either if it's their own system or if they want to look at some compliance circuits, they can actually insert the model into those simulations and they can enable the base plate capacitance couplings and they can observe the emissions of their system. Now, if there's any couplings or parasitics that are part of their system, it will be their responsibility to quantify those and include them, or maybe just try to understand, where they need to focus on minimizing those. But effectively, once you have your circuit built, you can start running some simulations. You can look at trends. You can compare it to emission standards, such as those here on the left. Here's some examples of some simulations that I've done. So on the left here, you can see this is actually the base plate leakage current in a boost converter simulation. So I've included the base plate capacitance and operated the system. And during one switching edge, where we have this high DVDT, we see current leak through the base plate. And it's actually quite substantial. In this case, we're looking at about a 5 amp magnitude. When we look at the spectral domain, again, we can look at trends. So here we have the gold waveform is if you ran a simulation without your base plate capacitance. And the more purple waveform is if you run the simulation with the base plate capacitance included. And the black line here is the limits for a mil standard 461 emissions limit. And, as you can see, so as we include the base plate capacitance, the emissions increase substantially. So if you were trying to run simulations to predict, if your system's going to pass compliance or, how much filtering you're going to need to add, you're absolutely going to want to include this coupling.
Brian, thank you for helping us to understand how Wolfspeed supports the design with the EMI topic. We appreciate your time today and thank you all for watching our test chat video. You can learn more about this and other topics on the Energy and Power section of the Richardson RFPD website. Simply follow our Ask an Expert link to submit your question related to the design challenge you may have. Thank you very much.
Thank you.